Okay, first I want to talk about our quiz policy. As I mentioned, our grading is kind of like a simple. We only have a final project. The topic of the project is related to our efficient AI, like papers or like research, right? And it's like this like final research topic is around, I think it's 20% of the whole grading. And besides this, 80% of the final project, we also have a 20% of is allocated to our pop-up quiz. Uh, for the pop-up quiz, we will have around 5 to 7 unannounced pop-up quiz throughout the whole semester. Uh, for the in-person section, you will write your answers on the paper and submit them directly during the class or like at the end of class. We would like to know that all the it's a strictly policy. There are no makeup for the missing quizzes. And because we all also have an online section for the students in the online section is asynchronized online section, right? But we would like the quiz to be a fair thing, right? I think you should for the students in the online section, you need to submit your answers within maybe 24 hours of the lecture or quiz being uploaded. Do you think is that okay? Yeah.
Question. So I saw this announcement like a couple hours ago, no, a few minutes ago actually, and I feel like that's kind of unfair for the in-person section. Like, first of all, the online section gets a whole 24 hours plus
Uh-huh.
any information at their fingertips to do the quiz. And then the in-person section, we get like a timed quiz that we have to write as well.
Uh-huh.
I feel like that's kind of unfair in terms of the two sections.
But how to what's your suggestion to make it fair?
I don't like, I feel like if you give one section 24 hours, you should give all sections 24 hours. I think
Uh,
that's the most fair thing to do.
I think that's not feasible. Uh, yeah, maybe we can think about how to make the online section of the pop-up quiz. Yeah,
And
go ahead.
something else, I was talking to a few people that are taking the class online,
Uh-huh.
and they raised some concerns about the fact that the quiz is they're only open for 24 hours because they signed up for the online section because it's supposed to be asynchronous. I know someone that that they're just unable to take the quiz depending on what day of the week it's gonna be posted because they have work, they have other responsibilities. The class is asynchronous. So I'm just wondering.
Maybe we can find another assignment for the online student besides the quizzes. Okay.
Can't you just make the assignment time once they start it?
Sorry?
You can just make the assignment time once they start it, so that they have the same time as they do in class.
Yeah, also can do that. We will
I
think.
don't know how long your pop quizzes are, like in person, it's like 3 minutes, or if it's like 30.
Yeah, we can make some like a time limitation for the pop-up quiz. Yeah, go ahead.
That actually goes a little into what I wanted to ask about. So what would this quizzes typically look like? Like how much time, how many questions, will it be open, closed notes?
It will be like closed notes, but all the content examined on the quiz will be covered during the content we present in the class.
How much time should you give?
It should be like 20 minutes. Okay, let's start today's course. The efficient machine learning course. Basically, the like in this class, I will talk about the general concept of efficient machine learning. We will cover several like very popular models and several mainstream solution for making those AI models more efficient. First of all, I want to give us a brief review about model compression and efficient AI technology. Basically, the model compression technology is to bridge the gap between supply and demand of AI computing, right? We can take a look at this demonstration. In 8 years ago, almost 10 years ago, our AI models is very small. You can take a look at the beginning of the transformer. It's proposed in 2017. The transformer model is very small. It's only 0.05 billion parameters, right? But within recent several years of development, the AI models becoming larger and larger, right? You can see the ChatGPT have proposed in 2018, and ChatGPT 3 was proposed in 2020, right? Those ChatGPT models nowadays have, in 5 years ago, already have hundreds of billions of parameters, right? Nowadays we have those very large scale AI models. They have trillion level of parameters in those large language models, right? But considering the supply of our computing, of our AI computing devices, like the NVIDIA's GPU chips, right? In 10 years ago, we have those V series NVIDIA GPUs, like V100, right? And after in 5 years ago, we have those A100 NVIDIA GPUs, right? And I think in 3 years ago, we have those H100 GPUs. And within recent 2 years, we have the GB series GPUs, right? This is GB 100, GB 200. I think nowadays we have GB 300, right? But those GPUs are very expensive. I think even for the A100 GPU, it costs 20,000. For the H100, it's around 4,000, and for the GB series, it's $500,000. Basically, the GPU is very expensive, but compared with the development, the trend of scaling up the large language models, the improvement of the GPUs is compared with this trend is still not good enough, right? And besides those NVIDIA GPUs, this H series, Google also have their TPU solution, right? This is a TPU solution. TPU V2, TPU V3. I think for nowadays, TPU have V7 series. Basically, I think for the mainstream large language models company, they only Google have their own TPU for large language model serving and training. But all the other companies like Meta, Amazon, OpenAI, Anthropic, like XAI, they all use the NVIDIA's chip solution. But no matter is TPU or GPU, we can definitely see the model. We can definitely see the trend of development of computational devices and the model computing requirement. So the model compression is the technology to break this gap. From basically the high level idea is to like this is like most straightforward training and serving pipeline. Basically, we train a neural network and then we develop those neural network on some hardware, and then we can realize those models inference. But with the help of model compression, we inject those model compression module into the whole pipeline. After we get the larger model, we can run some model compression algorithms like pruning, sparsity, quantization, knowledge distillation. There are so many. We will cover the details about those model compression algorithms in the following lectures. But the high-level idea after the model compression module is that we hope to get a smaller module. Like this, I think this model compression idea is proposed in like 12 years ago. Like after the like AlexNet, actually it's proposed very after there's a very famous neural network, convolutional neural network called AlexNet. It's not AlexNet, it's the net. It's proposed by Yuzhang, I think it's almost 40 years. And after Yuzhang proposes the LeNet, they directly propose we should using some compression techniques like pruning to get a smaller to slim the net. But it become a thing. The model compression become a thing. It's around 10 years ago. So first of all, we can take a look at what is pruning and what is sparsity. As we mentioned, I think these times of AI is started around 2015. After the AlexNet, everybody think like computer vision tasks can be hugely solved by neural network, deep learning, neural network related like deep neural network related technologies. And after this, since the like a deep compression technology was proposed, this is the optimal brain damage. This one is the method I mentioned the first work. Yuzhang proposed the first work. In this work they propose the neural network pruning techniques to prune the redundant neurons in the neural network. And this is literally the first work. And because it's like the trend of network compression and the network pruning is basically like very positively correlated with the trend of AI's development. You can see before, like in 50 years ago, is like only smaller amount of researcher pay attention to neural network compression, because it's like in 15 years ago, neural network is not that popular, right? It's not a common, like a community common, like a agreement that like a neural network is the final solution for AI. But after like in 15 years ago, some faculty, some researcher have those insights, and like similar to this trend, neural network compression becomes a similar thing. And basically, nowadays we can say that deep neural network, deep learning, is everywhere, right? But they are computational costly, so we should think about how to make how to make those deep neural network lightweighted and fast, right? Like in today's class, we will talk the deep learning in three dimensionality, in three aspects. First, the development in computer vision tasks. Second is the deep learning's development in language tasks. The third one is the deep learning in multimodality tasks. Okay, let's get into the vision task, because the vision task basically is in 15 years ago, vision task is like the most popular task in 15 years ago. Because like the Hinton's team, they proposed the AlexNet in 15 years ago, and like here, right? AlexNet is the first work using basically there's a Lacan has a student. There's three authors on the AlexNet paper. The first author is Alex. That's why we call this network as AlexNet. So when you're doing a paper, you think the paper will be very popular in the future, you should use your name to name after the paper. And the second author of the AlexNet paper is Ilya. Ilya is the guy who founded OpenAI, and in last year he have strong debate with Sam Altman, and have a huge thing with Sam Altman at OpenAI, and founded his own company recently. And the third author is Jeffrey Hinton, the Nobel Prize winner and Turing Award winner for inventing deep neural network. So basically, the AlexNet is it's a milestone paper in nowadays AI. This AlexNet, another thing about AlexNet is the AlexNet is targeting this task, the ImageNet task. ImageNet was proposed by Stanford team. I think this is like for nowadays we call ImageNet. We consider ImageNet as a data set, right? But initially, ImageNet is not just a data set; it's a challenge. It's proposed in 2009, and it's almost 20 years ago. And the team at Stanford, they collect a large data set for image classification. At that time, it is a very challenging task. I think in 15 years ago, the ImageNet, the researcher can only reach around 40% or 50% accuracy on ImageNet, because at that time, this is a very high resolution image, and in 15 years ago, we do not have good technology to recognize those high resolution images, to extract the patterns from those high resolution images. And realizing this classification task, I think before AlexNet, the mainstream solution for ImageNet is some SVM algorithms. But after AlexNet in 2012, like Geoffrey Hinton's team, they only use some some gaming GPUs. They Alex writes some CUDAs and using 2 GPUs to train the neural network on ImageNet, and AlexNet hugely improve the performance of on ImageNet. I think AlexNet they outperform other solution around 10 or 20% on ImageNet. This is a huge breakthrough on the computer vision task at that time. Yeah, and after that, the breakthrough of the AlexNet, people the researcher thinking that we can definitely handle the image classification tasks. So another topic related to our topic is efficient image classification, and here is like a demonstration about the efficient about the classification the classification neural networks. We have some very famous neural network architectures. We have the ResNet. We have the ResNet. We have the DenseNet. We have the InceptionNet. We have the MobileNet, and the x-axis is the computational cost about realizing one inference of the neural network, and the y-axis is the performance of those neural networks. It is the top one accuracy on ImageNet. The higher means the model have better performance, right? Basically, we can find the trend is that if we scaling up the computation during inference, we can if we scaling up the model's parameter size, we can get we can make the neural network get better performance, right? So at that time, what's the solution to break to break this trade-off? We hope to get to make the neural network have better performance while making the inference more efficiently, right? So the solution is neural architecture design, it's NOS. It's NOS. We hope to run some algorithms to search which kind of architecture we should use, and in this way we can get we can get a smaller neural network, but making those neural networks performance on image classification task good enough. So following this NOS solution, we also have some very famous neural networks like the EfficientNet. Also, we have the ShuffleNet, and we also have some once for all net. And all those solutions are widely used on some smaller neural network scenarios. For example, our nowadays we are using on our mobile devices. We have some for example, in our iPhone phones, if we using the photos, we can search on the photo, right? Those search can be considered as an image classification task, right? For example, we search on apple and dog, it will retrieve the photo on the photo on your photo algorithm, right? So the neural network we run is locally on our mobile devices, right? So those mobile devices, those neural network should be very small, should be very fast, right? Because our even iPhone is very advanced, but we do not like those iPhones, those mobile devices do not have enough computational source to run on very large neural network, right? So basically, those smart devices company they train lots of smaller image classification models and deploy those models on their on our mobile devices locally. Yeah, basically, thanks to those technology, those the efficient deep learning technology enables daily life application on our mobile devices, on our mobile phones, right? Like the photos application and many applications. Actually, except those mobile level, those smartphone level applications, we can even move the efficient AI, efficient algorithms further to more smaller devices. Like we can we can deploy those image recognition neural network on some MCUs, right? On some Blueberry Pi, on some FPGA. Those mobile devices only have a very small amount of computation capability, but thanks to the efficient AI technology, definitely we can deploy those algorithms on these edge devices on the MCUs, right? For example, we can deploy the image recognition neural network on those devices. And those devices can be very small, like the iPod device is smaller. This is like a extremely small usage of neural network is also widely deployed on our we cannot say daily usage, but definitely lots of usage like on some on the drones, right? On the drones, they have lots of detection, segmentation should be neural network should be run on the drones, right? So this relies on the efficient neural network to make all the things happen on the drones. Definitely, we have talked about a lot of things about making the models inference on mobile devices, on edge devices, like efficiently. They also have some training requirement for to be realized on the edge, right? So definitely, accept those efficient AI not just include the efficient inference, but also include the efficient training, right? So we can also realize the on-device training on the edge devices. For example, our mobile devices like our Siri, our Alexa, they are all edge devices. To initialize it, we need some samples to make it real, make it can distinguish is the instruction from our voice or from other people's voice. So it requires the devices can train a smaller network to realize that. So we like the efficient AI also needs those on-device training. And nowadays, a big breakthrough is that the promptable image segmentation considering the computer vision. And this is from the paper of the segment anything paper. This is the ICCV 2023 paper from Meta. And after this paper, some computer vision researcher said that the traditional 2D discrimination task in computer vision is solved because let us show the demonstration about what is SAM model.
Expressing my true self is powerful. I'm Jordan Childs, and I am a world-class gymnast. How do you get AI to recognize something like this?
Basically, you can realize any kind of segmentation, any kind of using just using some human prompt. This is a demo of the SAM paper. It's
For SAM 3D.
Yeah, it's for SAM. SAM 3D. Let me. Okay, this is a good demonstration. Basically, SAM can segment anything using some human prompt. Like a human prompt can be as like some variant prompt, like I just like click the dog, or can be used as a language prompt, like I said should segment out the dog out, segment the dog out. Basically, at that time, like in 2 years ago, many computer vision researchers said that those 2D, those 2D discrimination tasks is solved by using those SAM model. So definitely, but those SAM model is very costly. Or like I think the SAM model have billions of parameters on the neural network. So definitely because those discrimination tasks always should be deployed on some mobile devices, it's required to be efficient. So many people propose some like efficient vision transformer for the SAM model to accelerate the segment anything with some efficient vision transformer architecture. Basically, like for example, this efficient VIT works, they can comprise the SAM model around 50 times, and it can accelerate the SAM model around 50 times on A100 GPUs, accelerating it about 50 times, making the making the deployment of SAM model on the mobile devices totally doable. And we can see that if we run the vanilla SAM model on A100 GPUs, it can only process image like around 11 images per second. But if we use those efficient SAM method, we can process around 200 images per second. It's very fastly, and we can definitely make using those SAM models, those foundation segmentation models capability on our mobile devices, on our edge devices, right? And as I mentioned, like in 3 years ago, those some researchers thought that those discrimination 2D task is solved. So like there's another trend in computer vision communities that we are moving from discrimination tasks to generative tasks like we are more focusing on the generation task, right? So for example, we have those stable diffusion models, and we have those Sora models can generate very high resolution, very cool vision output of like images, high resolution images, or like very long videos, right?
Why did they do that? Why did they transition away from classification?
Like because in my opinion, I think generation task is more challenging. That's from the like academia's perspective, and more like from the commercial perspective, I think is that generative task is more commercially interesting for those companies. If they like the ChatGPT, like we can think about the language model, right? Like if we definitely our large language model can be also considered as a generative model, right? It can generate sentence, it can generate language, right? This language generative model shows it's very commercially interesting for those big companies. So
Classification would be more useful for like the medical industry, for imaging, for
yes,
robotics,
yes.
cars. I always thought classification would be more useful. That doesn't require as much computing power.
Yes, but definitely those generative models cost lots of computational resources. So here is an example, like for the like in 2 years ago, if we, I think it's like 3 years ago, the state of art of generative model is a stable diffusion model. To train those stable diffusion model is like in 3 years ago, normally it costs $1 million to train the 3 years ago's most state of art vision generative model. I think for nowadays, if you want to train a state of art vision generative model like the Sora level or Google's Veo3's level, the video generative model is cost like millions or tens of millions dollars to train it. It definitely 200 A100 GPUs is not enough for train those large scale video generating models. It should be like thousands of GPUs. But like generative models, especially those vision generating models, are more computationally expensive. The idea is that using those vision generative model, it need to if you want to generate a video, every image is very high resolution, right? Like the architecture of those vision generative model is normally the transformer, right? Transformer is computationally quadratic to the number of tokens, to the number of content you are processing. So for generative video, if you tokenize all the image, all the frames, and all the frames into tokens, it should be a very huge number of tokens, right? So it makes the vision generative model more computational costly. And also for the state-of-art framework for generating a video, generating a vision output, the method we are using is the diffusion model of flow matching model, right? For using the flow matching model or diffusion model to generate a vision output, you need to gradually remove some noise by running a neural network to do that. So for generating an image or a vision output, you need to run the algorithms, run the model for multiple times. This makes the like a generative model, especially vision generative model, very computationally expensive. Basically, we can see here, this is the 1 year ago's model. The cog video X is have around 6 billion parameters, but the computational cost is very high. And we can see here is the x-axis is for using the vision generative model to generate generated image with different resolutions, and the y-axis is the max. Max is the computational cost of generating one image. We can see that by scaling up the resolutions, the computational requirement also it's almost the quadratically increasing, right? So we need some efficient image generation algorithms, right? For example, like in the GAN, before the diffusion model, the GAN model, the generative adversarial neural network solution is the mainstream solution for generating image, and we can use some neural network compression techniques to reduce the size of those GAN model by I think we can do around 10 times, 20 times acceleration for those GAN models. And also, like in the diffusion model era, many methods have proposed to accelerate the diffusion model. We can definitely use some neural network compression algorithms like sparsity, pruning, quantization to make the vision generation through diffusion model more efficiently. Actually, this is the model like the pruning, quantization. Those are all model level acceleration method, right? Except those except those model level observation method, we also have some system level observation method, like in computer science, like in system observation, the most concept we are always using is the parallelism, right? So definitely we can accelerate the whole generation process. So this parallelism to accelerate the whole process. So thanks to the efficient image generation techniques, definitely, as I noticed, those algorithms, those neural networks are deployable on our mobile devices. That's why on our mobile devices, they have lots of like vision generation models we can use on the mobile devices on the laptop. Except those 2D or image or video generation, we also have like in computer vision, they also have some 3D generation models, right? Those they also use those diffusion models to create 3D objects from a reference image, right? Basically, there's a paper called 0123 is uh is like a zero training one image to 3D generation 0123. 0123 can using the diffusion model generate a 3D object. And most importantly, like especially last year, we have the video generation models, right? Those diffusion models can create realistic videos from natural language description, like Uh, like we have those View 3 models, we have those Sora models. Like it can generate very high resolution and around 10 seconds of like videos. But some researcher think that we can extend those models to longer videos, like minutes of level of videos or hours of levels of video. And another promising perspective of using the video generation model is that if we can, like the researcher thinks that if we can using the video generating model to generate the videos, we can predict what will happen in the future, right? So it can be considered as a world model, right? For example, if I fit this image, like I take I put it here. I put the cup here and take a picture and showing that I'm pushing this cup here and fit this picture to the video generating model and using the language as a prompt to say let the video generating model to show me what will happen in the future if I push this cup here and if the video generating model can correspondingly generate what will happen. For example, the cup will falling down to the ground and the water will like split out. If the video generation can follow the physical world to predict what will happen in the physical world, we can call those kind of video generation model as world model, right? I think many researchers are very attracted by this idea, those world model idea. But we are still like going to this destination. Like Actually, the concept, the high level idea of world model is like in many years ago, like maybe decades ago. But OpenAI, the Sora model, like 2 years ago, it's like those Sora model makes the whole thing more promising because before the Sora model, we cannot like not considering making the vision generation following the physical rules. We cannot using the vision generation model to generate a very realistic high resolution videos, right? So, but like the first step of the video generation is to making the video generation can at least generate some like looks like real vision output, right? So I think the OpenAI Sora model is the first model realizing this idea. That's why it makes the video generation task more doable, more attractive. Except those like high level generation task and discrimination task, the computer vision models can also do some like robotics, some control task. Like the most important thing is to like the have you ever tried the Tesla's SFD recently? It drives very smoothly. And Tesla do not have Tesla like on the car itself. It do not have some lidar sensors. All the camera on the Tesla is just some like a normal camera, common cameras. So basically, behind those Tesla's SFD, the perception algorithm is we need is to it need to realizing those 3D perception using the 2D cameras, using the 2D sensors, right? So we need like the algorithm is that we need to have some 3D perception algorithms. Definitely like those for those autonomous cars self-driving tasks, we hope the algorithms can respond as fast as possible, right? So in that case, we can make the real-time control of the cars, right? So definitely if we would like to realize those kind of like a real-time deployment of those 3D perception, 3D self-driving like a decision-making system, we also need to make those algorithms, those neural networks more efficient. Yeah.
Why would they remove the LiDAR from self-driving?
Because LiDAR is expensive.
Yeah, LiDAR is very expensive. Yeah, like I think the major company for self-driving in United States is Waymo and Tesla, right? I like Waymo use some LiDARs. I think the LiDAR is as expensive, at least as expensive as the car itself. Yeah, it's very expensive.
So that's like the main reason that they're just trying to do it normal camera.
Yeah, normal camera. So basically we need to realize some like efficient 3D perception algorithms using some efficient AI algorithms to make it deployable on the car itself. Basically that's a major task, not the major, but some promising tasks in computer vision task. And the second direction in deep learning in AI is the language, right? Nowadays, the language models is everywhere. Definitely is also powered by the deep learning technologies, deep learning based models. everybody knows the ChatGPT models, right? And the behind the ChatGPT model, the technology called is the large language model, right? Everybody knows the large language model are computationally heavy. Basically, we can we can feed every question we want to ask or anything we want. If we can format those things in language, we can input our thinking into the large language model, and then the large language model can correspondingly generate their thinking, their solution using the language, right? And the most existing breakthrough is the code generation task, especially in last year in 2025. For example, the Copilot by GitHub can making meaningful coding suggestion based on the context, right? And also we have more advanced coding agent like Cloud Code and Codec. I think Cloud Code is from Claude Anthropic, and Codex is from OpenAI. I want to ask how many of you have used those coding agents like Cloud Code, Cursor, and Codex? Okay, so basically half of you. Yes, for the resting half, I highly recommend you to try those coding agents. It's very useful and revolutionize. So what do you think about those coding agents?
They still have problems, but they work really good. And if you're learning a new language, it can get you on the right track and multiply the speed at which you learn the language or new system. So it's pretty good.
Yeah, it's pretty good. So I have another following up question is that if you need to pay for those coding agents, how much will you pay for those coding agents?
Currently it's $20.
Yeah, $20. Yeah.
Depends on the often that you use.
If you were starting a business, $20 a month would be pretty cheap for what it can do.
Yes, I agree.
To be honest, if you pay for Gemini 3 and then you download anti-gravity, you can get access to Gemini through anti-gravity.
Got it.
It's $20 to get both of them.
Okay. So basically, I code generation as a very big breakthrough. Commercially or academia, researchly, coding generation is a very big thing. And I think it will change many works in the not just in IT related domain, but also in other domain, because if everybody can use the natural language to generate code to solve their problem, some logic, the logic in many works will change, right? But the language model evolved very rapidly, but before the ChatGPT thing, before the large language model, the most important language related topic is neural machine translation in 10 years ago. Because people think that neural machine translation can bridge the language barrier. For example, we have two demos here. If we can translate the English into Chinese. We can translate the English into Japanese, and for nowadays, it's not common, but for people like in 10 years ago, it's totally a very big breakthrough in large in NLP. So this and definitely because like we hope those applications, those machine translation applications can be deployed on our mobile devices, right? That makes the user more convenient to translate for their daily usage, right? So to deploy those neural network on our edge devices, on our mobile devices, definitely we need some efficient AI technologies to like reduce the model size with for example, we have those live transformer. It can reduce the model size with pruning and quantization and like around like 20 times. This makes those like neural machine translation models deployable on our mobile devices. But if you can take a look at this year, like in 5 or 6 years ago, it's a big thing, because we do not have those large language models. After 2023, everything changed. Nobody care about those machine translation tasks. Like everybody is in NLP is more caring about the large language models deployment on the mobile devices. So for the large language model, the most important characteristic of the large language model is that it shows lots of zero-shot or few-shot learning capability. This is the major the major advantage of large language models. Let's think about what is zero-shot or few-shot learning capability in large language models. Basically, before large language models, if we want to realize a task like a machine translation, we need to train the whole. Like for example, if we want to make the large language model can understand like two different language, we need to train those models, right? If we want the large language model can understand some math problem, we need to use the math problems core like context to train those models. But for our nowadays large language model, we do not need to collect the corresponding data to train the models, right? Basically, we can ask the large language model everything. Like those questions, I mean, the large language model have never seen those questions in their training data, right? This is called the zero-shot or few-shot learning capability. So this capability is a major thing in the large language model. But it comes as a cost of the large model size, as I mentioned. Like those large language models scale up the model size from 0.1 billion parameters to several billion parameters to hundreds of billion parameters. And nowadays, those commercially used large language model have trillions of parameters, like thousands of billion parameters, right? This is crazy, but definitely by scaling up the model size, the capability of those large language model is becoming better and better. And another thing in the large language model is that the chain of thought. The chain of thought making the large language model can reflect their actions, the sentence they output, right? So it makes the large language model can process very complicated tasks, like our human beings, right? Our human being can solve those very complex tasks because we can draft, right? And we can turn off our like first version thinking and second version thinking, and we can reflect our previous thinking. This is in large language model. In the context of large language model, the LLM realizing whole thinking process using this chain of thought process. For example, this is an example. For this question, if we do not using those chain of thought, the large language model directly output this like the solution, but the solution is is wrong, right? But if the large language model can thinking, it will like thinking like this, right? They have the process about solving this problem, and the answer will be right. This chain of thought, this thinking process is very important in the large language model. But even though those large language models have very amazing capability, but it comes at a cost of large model size, right? For example, even though by scaling up the model size, the model's performance become better and better. But the model, the computational cost also increased a lot.
When you guys use quantization to reduce the size of LLMs, did you guys see that models started losing this type of like emergent behaviors that arise with the?
That's a good question. Yes, definitely. If you, it's also a trade-off by keeping the capability of large language models and making and get the efficiency good. It's like a trade-off. You need to propose some method to do some research to break this trade-off. Yeah, but definitely if you like just naively implementing some quantization techniques, like some vanilla technique quantization techniques to comprising the large language model, definitely you will lose some capability in the large language model. Yeah.
Explain that.
The high level idea is that the major computation in the large language model is the matrix multiplication, right? If you use the four position matrix multiplication, it's aligned with the distribution during your training. But if you, for example, you quantize the model, quantize the activation in the large language model, you will lose some accuracy. And yeah, go ahead.
So not of the building parameter model, what we do, we quantize the 100 billion to 50. Would be about 50 miles this model. Is one of these quantization that can be better to 50 or the
I think if you like, if you only comprise the model like about 2 times, it's quantizing the 100 billion parameters is better than the 50 billion parameters model. I think like the reason is mostly some empirical exploration. There are no like a theoretical explanation about why this happens. A hypothesis is called lottery tickets hypothesis. Is like some clear best paper, and the hypothesis saying that training a large model and then compressing it is like it's like buying a lottery ticket. First you train the model and then you compress that. It's like you make the pool smaller, so it's more likely you will get the lottery. Okay, I think this is today's course, and let's see you next week. Bye bye.